Okay, let's get started here. So we're gonna do a quick recap, and then once we're done, I don't think it'll take us too much time to wrap up our packet here. I'll pass out the study guides. It has everything but the proofs that will show up. And I'll actually talk more about that probably later this week, and you'll get the actual proofs by latest on Friday. And I'll also be posting them, so if you're not here, you will have that. Yes, I think that's all. Oh, I'm still grading quizzes. I'm a little behind. So I'll try to get those done. Even if like actually when you guys are working, I might do some grading so that you guys can have it by the end of today, but at latest I'll have it done for tomorrow. Aiden, I know you won't be here, so I'll actually have yours. I graded yours first so that I can have that done. Yep. Okay, so let's look at what we did last time. So just kind of a reminder, we did an example where we could use synthetic division, which is much faster. And also you can still use this when you're doing like a ZP or a ZN and not just like with real numbers. You are allowed to use this method. But again, it's only when you're dividing by linear terms. And actually the nicest and the only form that we really did it is linear terms that look like x minus the root instead of the general form ax plus b. So we're assuming it's monic and it's linear here. So just as a reminder, right, if the polynomial we're working with is this guy here, 2x squared minus 5x. No, it's 2x cubed minus 5x squared minus 6x plus 4. You want to put placeholders anytime you don't have an x or a coefficient showing up. It will make a big difference if you don't do that. Here we found x equal to 1/2 was a root. So I don't think x minus 1/2 is the factor. I think x equal to 1/2 is the root. And we bring down the 2. This is going to be the coefficient on my x squared. I really go down a power. So this was supposed to be degree 3. So it'll be degree 2, 1, 0. And anything remaining should be your remainder, should be 0 if it is a factor. We multiply it by the 1/2. Anytime I go up, I'm multiplying by my 1/2. And I add these numbers, do the same thing, add my numbers, do the same thing. And if I don't get 0 again, then I either didn't find a correct root or some of my calculation here, something went wrong. Okay, but just as a reminder, because this is much faster way to do it, although it's equivalent to your long division as well. Okay, it turns out that when you can write a polynomial so that's all the way reduced and you only see linear factors showing up, we say that it splits. In that example, we saw that we got a quadratic that was actually irreducible. So that specific example, it does not split because the whole thing doesn't just have linear terms. And I can even say that this one doesn't split also. Okay, we went through another example, again, showing our polynomial was irreducible. We first checked for linear factors. Because this has integer coefficients, I can use my rational root test. If it was rational numbers coefficients, I clear out my denominator and really work with its associate to find roots there. And then I can use my rational root test. We found that none of these gave us back roots. And for that reason, I can't have any linear factors. The only possibilities are going to be quadratic. Okay, and if I can factor over the rational numbers, that actually tells me I can factor over my integers. So it really helps me to kind of condense the possibilities I can have for my coefficients. And so if I can factor it with quadratics, I should have irreducible quadratics because they shouldn't be able to factor with linears or else I'd have a root. And we did some brute force work here because nothing else really would have worked. We saw up above, right, it was degree 4. So showing that it's irreducible like mod P actually would take some bit of work. It would look pretty similar to this. And we didn't have our Eisenstein yet, but we couldn't use it here either because we don't have factors for our non-leading coefficients here. Okay, but we went through all this work, remembering that all our coefficients are integers, and we could actually assume that the leading coefficients were 1. If they were -1, I can pull them both to the front, and then we just change it to minus c minus d, but they're still integers, so it's fine to write it this way. We ended up having a contradiction with one of these equations here after factoring it all the way through, or after foiling it all the way through, expanding it. and setting it equal to the original polynomial, and then setting our coefficients equal to each other. We got some contradictions where one of our coefficients had to have been an irrational number, so not an integer, and so we wouldn't be able to do this here. Okay, but working with our integers really reduces the possibilities that we have. So remembering when I can factor in Q, that means I can factor in Z. That really helped us with these cases showing up here, right? So this brute force method is most helpful when we have low degree of at most 4, because if it's 2 or 3, we just find roots there. If we can't find a root, then it's irreducible. If we can find a root, then it's reducible there, as long as the coefficients come from the field. Okay, then we learned Eisenstein's criterion, which is my favorite one to use because it's to me the easiest one to use and kind of the more obvious one to know when it's applicable. And it takes the least amount of work to show irreducible over the rationals. So here, if I have a polynomial degree n, and I believe actually this should be, yep, these should be integer coefficients because I'm thinking about factoring. So I'm going to have integers showing up here. If I can find a prime, which I can't always do, but if I can find a prime where the prime divides all the coefficients except for the leading one, that's what number 1 and 2 are saying. And if I square the prime, it doesn't divide my constant coefficient. Immediately, I know it has to be irreducible over Q. So the things that we look out for are the factors of our leading coefficient. And really, I can focus on my constant one. I can think, what are the factors, the prime factors? I don't want the prime that I choose when I square it to divide 12. So 2 immediately is not an option. And then I check, does 3 work for the rest? It does. And it doesn't divide the leading coefficient, which is 1. So immediately I know with P equal to 3 and Eisenstein criterion that it's going to be irreducible over Q. Right? I might not always be able to find a prime, but I at least now have a finite set of primes that I can check. Unlike with our mod P irreducibility test, I don't know which prime is going to work in those cases. I really have to study those deeper, and I don't know when to stop. Right? But this immediately tells you, here are the possible ones, check which ones work, and it doesn't take that much work to actually do that process there. Okay, so these are great when you can find a prime, but you can't always find one. And so the very last method that we talked about was shifting our polynomial, because it turns out if I shift my polynomial, so if I plug in x plus a instead of x, if the shift is irreducible, then so is the original, and vice versa. So getting information about a shift actually tells me about the original. And it turns out that sometimes Eisenstein doesn't work for the original, but it does work for some shift. So these are really the hardest ones to kind of figure out what to shift it by. So almost always you'll see, like, I mean, we don't really have anything left, but on the final, if you have something that needs a shift, I'm going to tell you explicitly find a shift here or use a specific shift, and maybe tell me why the original won't work, but the shift will work. You'll actually see a problem in the study guide that look exactly like that. But these are the hardest ones. These are very hard for me to like figure these out also. So I won't expect you guys to just be able to see them, try all your tests, and eventually use the shift test here, the method there. Okay, but we did an example where we shifted by 1. And then once we simplified it, we saw that all of our non-leading coefficients were all even. So they all divisible by 2. And my constant was not divisible by 4. So 2 for Eisenstein criterion actually works. And I can show it's irreducible here. And so really something that we'll notice in a lot of these examples is we'll have polynomials with leading coefficient 1. So it makes it kind of the nicest because no prime is going to divide it. So if it works for my non-leading coefficients, so if number 1 and number 3 are true, number 2 is immediately true if it's monic, if it's leading coefficient 1. So you'll definitely see some of those come up pretty often. Okay, last thing we did is we worked with our quotient ring where the ring came from polynomials where the coefficients are from Z2, so 0 or 1. And then we're modding out by an ideal generated by x squared plus x plus 1. So we can really treat the polynomial and the ideal as our 0 element. because anything that's a multiple of it is really going to look like the zero element or zero representative inside of our quotient ring here. So we can do some manipulations on this polynomial to help us to decide how many do we actually need here, how many representatives do we need, what's the biggest degree that will really show up. Here we can show that x squared, a degree 2, can be reduced down to degree 1. We can actually do something similar for degree 3. We can reduce it to a degree 0 or a constant. And so really anything above 2 is redundant. I can write it using my linear or my constants. And it turns out that these are all the ones that you need. Something else that we can think that I didn't write out earlier, so you can actually think division algorithm. Technically, I shouldn't be able, oh no, this is a field, Z2 is a field, so I can't think division algorithm where my coefficients come from Z2. I can think when is my representative equal to the zero element? It's when it's a multiple here. The only time it's a multiple is when I divide and my remainder is 0. And so I can get some information about when that's possible, or I can also think when are two representatives equal to each other, when their difference is a multiple of your x squared plus x plus 1. But that would mean that it would have to be, right, when I multiply them together, it would be at least degree 2 here, because my degree won't go down. Okay, but we looked at our table after deciding we only had 4 possibilities. This is really nice because the coefficients come from a finite field. I was working with Z. I could still have a bunch more representatives, and I would have to decide, do I have infinitely many? Do I have finitely many? And which ones are going to be the same? And so we went through the tables, and what we found for the multiplication was that we found our unity show up in all the columns and rows that are not my 0. And so what does that tell me about the quotient ring that I'm working with? What can I say about our quotient ring here? Right. What type of ring is this? It's a field. I already know it's commutative. I already know it's unity because it has 1. Bless you. And my non-zero elements have multiplicative inverses inside of the set. Where I'm seeing the unities are the ones represented by 1 here, right? So this does give me back a field. Okay, and something else that we can say here is something about this specific ideal or polynomial that we're using. In Z2, do we know, is this reducible or irreducible? And this is easier to check because it's degree 2. This one's irreducible. If I plug in 0, if I plug in 1, I don't get 0 back out. Because it's degree 2 coming from coefficients from a field, immediately I know it's irreducible. And so actually I can say something more general than this. It turns out that when I have a field for my coefficients and I mod out by an ideal generated by something that's irreducible, I'm always going to get a field back out. So here, right, it turns out that this holds in general, which is really saying if we have F a field and P is a polynomial where the coefficients come from F is irreducible, then we know if we look at this quotient ring, it's always going to give us a field back out. Okay, and I think I might skip out on this proof. You can find it in the text. I might just write it up and post it within the notes if you guys want to see like the full proof out. But I want to make sure that I give us enough time to do some practice on some of these problems. Bless you. But it's exactly what we were just saying here, that if I have coefficients coming from a field and I have an irreducible polynomial, oh, actually, this is like one step before that. It turns out that these irreducible polynomials give us back maximal ideals. And this maximal ideal is going to give me information about my polynomial ring over the maximal ideal, it's going to give me back a field, right? So really I need one step before I can say this, but I'll post the proof for this if you guys are interested in seeing what this looks like. But we'd have to break this up into cases, and we'd have to do an if and only if, so we'd have to do 2 directions on this. So I think it just might take up too much time. I wanted to get some more practice doing some more problems. Okay, great. So some things that we can say is, in this specific case where we have a commutative ring with unity, our maximal ideals are going to be prime ideals. And so we can almost think these irreducible polynomials work like primes, work like prime numbers. That's the smallest it can get in terms of factoring. So these irreducible polynomials give maximal ideals. And in our case, that implies that it's a prime ideal as well. Okay, so if I take 2, let's say f and g, and naturally let's say h is your irreducible polynomial, and f, x, and I take 2 polynomials where, and actually I'll call it p, because we're going to think about this as a prime, where I can write p, where I know p divides the product f and g. This is a fancy way of saying f and g is a multiple of p, or f and g is in the ideal generated by p. But because it's a prime ideal, because I know it's maximal, I know that either f is in the ideal generated by p, or g is in the ideal generated by p, which is another way of saying p divides f or p divides g. So again, this is the same as thinking f is in the ideal generated by p, or g is in the ideal generated by p. This is the reason why we call them prime ideals. It's because really we were generalizing this idea of being prime inside the integers. But now we can think of these irreducible polynomials almost like these primes, the smallest that you can get when you're factoring. And as soon as I know a prime shows up in some factorization, then it has to factor one of the pieces there. It can't be split up in some nice way, right? If it was like 4, maybe I could have 2 in one and 2 in the other. But if that was 2, I'd have to come from one of them or both of them. Okay, but really these irreducibles are the smallest polynomials you can have in these polynomial rings. Okay, and really this theorem is just like an application of the last one, with the fact that we know if I have a maximal ideal inside of a ring that's commutative with unity, then when I mod it out, I should get a field back out, right? So as soon as I know it's irreducible, I know the ideal generated by it is maximal, and so then I know my polynomial ring modded out by the ideal has to give me a field back out. Okay, and what we're gonna see is examples where this is happening, where we have fields of different sizes that we haven't seen before. Actually, in the example we saw previously, we have a field of order 4. And so far, the fields that we've seen have not had composite order. It's had prime characteristic. That's not going to break in this case here. But we haven't seen an example yet where the order wasn't a prime or wasn't 0. So this is giving us some more ways or some more orders that can show up for our fields. Okay, so previously the types of fields that we had were things like the rationals, the reals, complexes, right? Integers didn't work here. And these had characteristic 0, and these were all infinite. Those are not synonymous with each other, but in this case, they both are infinite in characteristic 0. And then some finite ones that we had, the only ones we've seen really are our ZP, where P is prime. So this is finite characteristic P, where P is prime. Okay, so again, we do know the only characteristics possible are zero and P. That's not going to change, but we are going to have different orders showing up other than infinite order and prime order, right? We already saw one example of 2 squared or 4 showing up here. Okay, so if I think of a field K, we're going to go through the possible orders and see if we have any examples of these. Anytime I see a prime showing up in this list, I know I can use ZP as an example of a field with that specific order. So here I'll get Z2, Z3. This is the example we just saw, order 4, which is our Z2x mod x squared plus x plus 1, where the polynomial was irreducible. If it weren't irreducible, we won't have this fact. 5 will have Z5. Oh, I skipped 7, which is Z7, right? All our primes, we can do this. So we're actually going to have a recipe to find more powers or more orders showing up here. Not all of the ones showing up here will work, but things like 8, 4, 9 are going to work. And we'll see the relationship between where the coefficients come from and what the degree of the irreducible polynomial is. Okay, so here, what we're going to do, and this is really going to help you answer that first problem on the homework. This is the only thing that was missing to do that. We're going to find a field of order 8, which we'll notice is not prime. But what we will notice is that this is a power of 2. It's 2 to the 3rd power. We're going to find a field of order 9. This also is a power of a prime. Right? I only have one prime showing up in this decomposition. I don't have more than one prime. Okay, so what I can do here is I can come up with a field for my coefficients, turn it into a ring, and then mod out by an irreducible polynomial there. So I have to be careful that I can find one. It'll give me back a field. Finding the order is going to be hard, but actually we'll see exactly where that information is coming from. So here, because my prime is 2, I'm going to think coefficients come from Z2. Okay, and the thing I want to mod it out by is an ideal generated by an irreducible polynomial where the 3 comes from the degree of the irreducible polynomial. So if I can find an irreducible polynomial in Z2, then I'm golden. This is a field, and this is actually going to match up exactly like this. So here, this is the prime showing up, and here I want an irreducible polynomial of degree 3, the power. Okay, can you guys think of a irreducible polynomial in Z2 of degree 3? Did you say this? To 3rd? Oh, yes, degree 3. Do we have a squared in there? Okay, let's check. This is really easy to check because it's degree 3, right? Degree 3 or 2 from coefficients from a field. You just plug in all the elements. If there's no roots, then you know it's irreducible. Here, when I plug in 0, I get 1. Here, when I plug in 1, I get 3, which is also 1. And so this is irreducible because all my, when I plug in any of my elements, I don't get a root. I don't get 0 back out. Okay, so here is an example of a field of degree 2 to the 3rd power, or order 2 to the 3rd power, which is 8 here. So again, I take Z mod the prime, because it's always going to give me a field. That's why I match it up in this way. And then find an irreducible polynomial that has degree of whatever power shows up on that prime. And this formula is always going to work. If I have infinite groups for my field, this is not going to work. I'd have to do some work to see, do I actually get a finite field there, or do I still get infinite? Okay, so let's think in here. If I want order 9, what should I be working with in terms of my coefficients? Z3. So again, I take my prime. Okay, and I'm going to mod it out. And we have options, possibly. I want what kind of polynomial? We want quadratic, Really, this is degree 2. And irreducible. Again, because we're doing this over a field and it's degree 2, it's really easy for us to actually check that it's irreducible. If it was degree 4, or if I had something like 3 to the 4th power, it would take a lot more work for me to be able to decide that it's actually irreducible. We can do that, but this is much faster if it's degree 2 or degree 3. Okay, can you guys come up with an example here? And we can stick with monic. Okay, let's think +1. If I plug in 0, I get back 1. If I plug in 1, I get 2, which is not 0 mod 3, so it works here. Right, I didn't have that many options on this one. I don't want the constant coefficient to be 0, or else 0 is going to be a root. If I did 2 here, when I plug in 1, I would get a 0, so that wouldn't work either. But possibly I could have an x showing up as well. Okay, but again, this degree equals the power that shows up on that 9 equal to 3 squared. Right? And the prime 3 is exactly the prime that we're using on my ZP, right? Because if I use the power instead, it doesn't have to be prime, and then that doesn't have to be a field, and then I don't have all my nice theorems in terms of the coefficients coming from the field. Okay. Let's look at one other example. This one's not going to be finite, but we are going to be able to give some information about it. Okay. What can you tell me about this polynomial over Q? Is it reducible or irreducible over Q, over the rationals? Okay, and why? Feels obvious, but okay. And how can we show that it has no zeros inside Q? Just because we find zeros doesn't mean that those are the only zeros, right? Like when we've seen like with integral domains, when we have zero divisors, like with Zn, we could have multiple zeros that don't add up to my total n here. So what are some ways that I could prove that statement? Aiden?
I was saying 7 equal to 0 and simplify x.
Right, but just like with like ZP, we'd have to think about what do we mean by square root, and maybe there's somehow that we can do some manipulation to actually see that. Like these are just symbols. So it's things that we could do here. Is Q is a field, and so if I don't have any roots in my rational numbers, immediately I know it's irreducible because it's degree 2, and I have my rational root test. My rational root test tells me the only possibilities I'll have are plus or minus 2 and plus or minus 1. Plug those in immediately, I know I don't have any roots inside my rationals. So there's ways to kind of connect all these ideas to make sure that we can fully prove that this is irreducible over the rationals. And I'm going to start, you can do this to say over Q instead of writing over Q. I keep forgetting to say it. I regret it every time I have to say over Q. Again, rational root test. Q is a field. And this is degree 2 altogether. We can get this information. Also, because Q is a field, I know I have to have exactly 2 zeros, including multiplicity, right? So if I find zeros, that's actually a way that I could have proven that as well, is using my theorem that tells me about the number of roots that I'll have showing up there. Okay. Great. So this is irreducible, which tells us that if I take Q as my coefficients for my polynomials, and I mod out by this irreducible polynomial, I will get back a field. Okay, but which one do I get? We've seen some examples like this in the homework, where there's really nice maps that help us kind of see what this will be isomorphic to. Can you guys see what it is? what kind of maps, right? Because I can even use fundamental or first isomorphism theorem. So I'm going to use QX to be my domain, and I want this to be my kernel. What is it? Nope, not integers. Q adjoin root 2 or Q with a brackets root 2. Okay, I have a map here. Anytime I start with polynomials, there's a very natural map that says plug in a specific element into all my polynomials, and it's going to land in a specific place. Here, if I want this to be my kernel, I need all the things in here to go to 0. So I need to find the roots of this polynomial and be the thing that I plug into my function here. So this is why I use root 2 here, is because the map is going to take f to f of root 2. Okay, the only things that we're missing, right, really when I plug in root 2, I'm going to have rational numbers floating around and root 2s. So I have to be inside of Q root 2. Possibly I don't get the whole ring, but you can actually show that this is surjective, a ring homomorphism, and that the kernel is equal to what? X squared minus 2. Okay, I could show no polynomial of degree 0 or 1 is in the kernel. This polynomial is in there. Because my coefficients come from a field, this polynomial ring is a PID. So any ideal is going to be generated by one polynomial or can be generated by one polynomial. If I find a minimal degree polynomial, it generates it. So I can show by showing that degree 0 and degree 1 are not in the kernel, that this is exactly my kernel, instead of doing double containment for my kernel here. Okay, so then first isomorphism theorem tells us that this here is going to be isomorphic because this is surjective to the following. This is a field here, and so this guy has to be a field, which we didn't previously know, or we didn't really look that deeply to see if we got a field. If I had z adjoined root 2, definitely not a field. I don't have inverses, but it turns out for things like this, a plus b root 2, where a and b are rationals, you can find multiplicative inverses, which is really the only thing that we would have to be careful about. It's commutative, it has unity, it's definitely a ring. So the only thing that would be missing is to show the non-zero elements have units or have inverse, multiplicative inverses. And you can actually show if this is non-zero, if one of A or B is not equal to 0, you can explicitly say what the multiplicative inverse has to be. Okay. Great. Oh, let me give us a couple more examples here. Following the same idea. We're going to see that Q adjoined root 6 is isomorphic to what? That's going to be my ideal, what I mod out by. So I'm going to take the ring QX and mod it out by the irreducible polynomial x squared minus 6. Okay, I can do this with different fields. I can think here, z mod 3, a field, adjoin root 2. I want to think what kind of irreducible polynomials have root 2 as a root, even though I'm living inside z3. Here I can think z3x. And here I can think x squared minus 2. This ends up being irreducible if I plug in, this is the same as x squared plus 1. If I plug in 1 or 0 or 2, yes, I don't get 0 mod 3, so this is irreducible. So I can really think, what are the roots that are missing that makes this irreducible, that doesn't live here? Attach it to this field, and it gives me the same field back out. Right, this really is thinking, you can almost think, how could I extend this field so that it makes this reducible? What roots do I have to add to make this part reducible instead of irreducible? Okay. right? So again, these are really called field extensions. I think take Q, how can I make it bigger? How can I make it a field that holds Q in it, but now makes this reducible? I really need to add the roots in here. Okay, and the last thing that we'll say here is, and really we won't do too much work in this, but maybe I'll make these comments actually here. Well, x squared minus 6 is reducible over this new field that we found. And we had x squared minus 2 is reducible over this field now as well. Okay, some questions could be, if I take any irreducible polynomial in Q, how far out do I have to go? Right, if I want to think I want all the roots to all my polynomials, how far do I have to go? If I take polynomials inside the integers, how far do I have to go so I can make sure I have all my roots? In terms of integers, as far as you have to go is the rationals, which is really nice. That's why we have these nice theorems that go between the integers and the rationals. If I know something about integers, I know something about rationals and vice versa. In terms of the rationals, there's not a nice name for whatever field that is. You don't have to go as far as the real numbers. Things like e and pi are not going to be roots of polynomials that have coefficients in the rationals. And what do you guys think for the real numbers? If I had coefficients with the real numbers, how far do you have to go so that it makes all the roots show up so everything is reducible? Complex numbers. Immediately we know x squared plus 1. We need plus or minus, or we need I to show up there. It turns out you don't have to go any further, right? That's as far as you have to go to get all of the roots if your coefficients are coming from the real numbers. This is something called an algebraic closure. It tells you how far, what's the smallest field you need so that all your polynomials are reducible, so that really you have all the roots of your polynomials there. Okay, this is one reason why when you have real coefficients, you can, if I just want to use real numbers, I'm either going to have linear terms or quadratic irreducibles, where the quadratics have complex roots, and they really come in complex conjugates. So there's a lot more theory that goes behind here, but it is pretty deep to even like get to that level to see how far you have to go. But we are kind of seeing some of these connections on how can I make one polynomial reducible? I really am missing the roots. I just add the missing roots inside of there. Okay, but that's where we're going to take it. So if you guys don't have any questions, I'll pass out our study guides here. Yeah, but in terms of the homework, those examples that we did with times to powers was the only thing that was missing. So they're actually pretty easy to come up with examples. And you guys have homework questions, don't I believe you only need the complexes to, yeah, those are all the roots that would show up. Yeah, the algebraic closure of complex is complex, I believe. Yeah, at some point it kind of has to stop. Yeah. Or it feels like it kind of has to stop. Yeah. Okay, so I'm also gonna do some